Hi everyone. This video is about concurrency. So when you have three or more lines that intersect in a single point, we say that those lines are concurrent. Concurrency is an unusual or rare situation. In general, if you have three lines in the plane, they might look something like this, where the lines would intersect in three pairs. So you have a pair intersecting here, and a pair intersecting here, and a pair intersecting here. This is the so-called general position of three lines in the plane. It is unusual, then, that those three lines would intersect in a single point. When that happens, we say that the lines are concurrent, and that that point of intersection is the point of concurrency. So our interest is in some really remarkable concurrency in triangles. So the first concurrency you were asked to explore in your GeoGebra assignment is the concurrency of the medians of a triangle. So recall that the medians of a triangle are the segments that connect vertex to opposite midpoint. So here we construct all of the medians, and as you can see, the medians are concurrent at a single point. And you can move this triangle around, and no matter what you do, the medians will always be concurrent at that single point. And that point is called the centroid of the triangle. The centroid has a number of remarkable properties. Here I have some side lengths shown here. One of those properties is that the centroid divides every median in a 2-to-1 ratio. So CG to GZ is 2-to-1, and AG to GX is 2-to-1, and so on. And so you can see that here in the segment lengths I have at the bottom. There's some rounding error here in the way that GeoGebra computes these lengths, but you can see that the ratio is 2-to-1 in each case. Another amazing fact about the centroid is that the centroid is the so-called center of mass of the triangle. If the triangle were a physical object, then this is the place you could balance that physical triangle on your finger or on the tip of a pen or something like that. It's the center of mass. And in fact, all of the medians are essentially balance lines for this triangle. The second concurrency I had you explore is the concurrency of the angle bisectors. This is another remarkable concurrency. The angle bisectors are concurrent at the so-called incenter of the triangle. The incenter is the center of the inscribed circle of a triangle. Every triangle has a unique inscribed circle, one that you can draw that is tangent to the three sides of the triangle, and that circle is centered at the incenter. So the reason for that, and I'll show this in a guided proof later this week, is that the angle bisectors themselves are sets of points that are equidistant to the two sides of the angles that they bisect. So for example, if you have a point right here on the angle bisector of BAC, this point H is the same distance to AB as it is to AC. And when you put all three of those angle bisectors together, you get a point that's the same distance from AC as it is from BC as it is from AB. And since that's the case, you can make that a radius, and that gives you the inscribed circle. And so this is the incenter. The last concurrency I had you explore is the concurrency of the perpendicular bisectors of a triangle. This is, I think, my favorite. It's a really beautiful one. Similar to the incenter, this is the circumcenter of the triangle. It's the center of the triangle's circumscribing circle, the circle that passes through the three vertices. In fact, the existence of a circumcenter, the existence of the point of concurrency for the perpendicular bisectors, proves that every triangle can be inscribed in a circle. All you have to do is construct the circumcenter. And as it turns out, the perpendicular bisectors intersect in a point that's equidistant to the three vertices. And this has something to do with the fact that perpendicular bisectors are sets of points that are equidistant to the endpoints of the segment they bisect. For example, this perpendicular bisector right here is all the points that are equidistant to A and B. So every point on this perpendicular bisector is the same distance from A to B. Every point on this perpendicular bisector is the same distance from B to C. Therefore, the place they intersect is equidistant to all three of the vertices. That means that you can take that distance to be a radius and construct your circumscribing circle. One of the interesting ways in which the circumcenter is different than the incenter and the centroid is that the circumcenter can be outside of a triangle. And in fact, it could be very far outside. And that could sort of pop back over here. You probably explored and noticed that the conditions under which the circumcenter is inside the triangle is if the triangle is acute. It's outside the triangle if the triangle is obtuse. And in the special situation that it's on the triangle, that is when the triangle is a right triangle. And this probably reminds you of a couple of different theorems. One, there's the theorem that says that the midpoint of the hypotenuse is equidistant to the three vertices of a right triangle. We proved that a couple of weeks ago. And then there's also this theorem that says if an angle is inscribed in a semicircle, then that angle is a right angle. And what we're seeing here is that for a right angle inscribed in a circle, the hypotenuse is always a diameter. So that's a little bit about some remarkable concurrencies in triangles. There are more, and we'll see some of them in some extension activities later this week.